Hello to everybody. Today we are gonna solve the problem 4 of bending and axial load. Okay, we have the following statement: two short posts with solid circular and rectangular cross section respectively are loaded as shown in the figure. We have P, force applied in the vertical direction in this corner and in this edge of the two cross sections. The diameter of the circular post and the width of the rectangular post are equal to D, and the question A is to determine the dimension B of the rectangular cross section in order the maximum tensile stress is the same for both posts. Okay, so we have to look for the point with maximum tensile stress, and if we look to this eccentric force, we realize that this point is opposite to the point where the force is applied. Okay, so we are gonna translate the forces to the centroid in each case, and then we are gonna write the expression for the normal stress sigma nx in the round cross section is equal to P minus P divided the area of the circular cross section plus P multiplied D divided by 2 when the moment of inertia about, let's say, the z-axis, and multiplied by the y coordinate. Okay, so in this case we have here the y-axis, this should be the y-axis, and this is going to be the z-axis. So we assume that we have this this distance to z, d divided by 2. So we have compression in positive y here, so this sign should be minus. Okay, this should be minus. We change it and we leave a minus here. Okay, minus. Okay, so this is gonna be equal in y equal to minus d divided by 2. It's gonna be equal to minus p divided by p d divided by 2 square minus p d divided by 2 number p d divided by 2 to the 4th power 1 divided by 4 and multiplied by minus d divided by 2, and the result of this is equal to minus 2. Sorry. This is equal to minus p divided by number p d divided by 2 square, and we have these two here, so minus plus 4p divided by number p d divided by 2 square. So the result is 3 multiplied by 4p divided by number p and d square. Now, if we calculate the maximum normal stress for the rectangular cross section, we have minus p divided by the area of the rectangular cross section minus p d divided by 2 divided by the moment of inertia about z multiplied by the y coordinate, and this is going to be equal in the point with maximum tensile stress equal to minus p divided by b multiplied by d. B is the unknown, okay, is this dimension that we want to calculate, minus p divided by 2 divided by d cubed multiplied by b divided by 12 is the moment of inertia of the rectangular cross section with respect to the z-axis. Okay, this is again our z-axis, and this is the y-axis. Okay, right. So we can write this moment of inertia about z and multiply it by minus d divided by 2. So the result is minus p divided by b divided by d minus plus, we have d divided by 2, d divided by 2, that is for 3 plus 3p divided by b d. And the result therefore is 2p divided by b d. So according to the condition that we have here, both of them are equal, so 12p divided by number p d squared is going to be equal to 2p divided by b d. Therefore we can calculate the value of b as 2p divided by d multiplied by number p d squared divided by 12p. Okay, so we can cancel p. We have 1d that goes to 1, and the result is number p diameter divided by 6. This is equal to b. Okay, this is our solution. Okay, in the second question was to determine the compressive stress in the post. So what we have to do is, again, we need to calculate the normal stress sigma x in the round cross section, but in this case in y equal to positive d divided by 2. So this is equal to minus p divided by number p d divided by 2 squared minus p multiplied by d divided by 2, number p d divided by 2 to the 4th power divided by 1/4, and multiplied by d divided by 2. Okay, so in this case we have minus p number p d divided by 2 minus 4 p divided by number p d divided by 2 squared. So this is 5 that multiplies by 4, so 20p divided by number p, the diameter, minus compressive stress. Okay, this is the maximum compression stress in the round cross section. Now we do the same for the rectangular cross section. Okay, y equal to d divided by 2, so we have minus p divided by db minus p d divided by 2 d cubed multiplied by b, everything divided by 12, and multiplied by d divided by 2. So what we have here is minus p divided dv minus 3 times p divided by d. So this is minus 4 p divided by dv, and if we write the value of b we have calculated before, that is number p d divided by 6, we have minus 24 p divided by number p and d squared. This is the maximum normal stress, negative, that is compressive stress in the rectangular cross section. Okay, and the last question that we have to solve is to determine and represent the neutral axis in the circular cross section. Okay, so we have to look for the neutral axis in the circular cross section. If we draw again this circular cross section, we have our axis. This was the y-axis. Y-axis is the z-axis pointing upwards, z-axis, and we have, if we represent here the normal stress, we have a maximum of compression here, okay, that was equal to a certain value. We have a minimum tensile stress here that was lower, so what we expect is that the neutral axis cuts the cross section somewhere in the negative value of the y-axis. This was as we saw before. This was 20p minus 20p divided by number p d square. Okay, forgot here that square, this square, and we have here this value that was equal to 12p number p d square. Anyway, if we want to calculate the coordinate, the y coordinate of the neutral axis, okay, we have to calculate the normal stress sigma x equal to minus p number p d divided by 2 square minus p d divided by 2 p d divided by 2 to the 4th power 1 divided by 4, and this is the y coordinate of the neutral axis when we make this equal to 0. Okay, so y of the neutral axis, I will use neutral axis, is equal to minus p divided by p d divided by 2 square multiplied by number p d divided by 2 to the 4th power 1 divided by 4 and divided by p d divided by 2. This results in minus d divided by 8. Okay, so this is more or less the neutral axis. Okay, and this distance here, this distance is d divided by 8.